Welcome back to the lab. Today we're going to talk about inverter output stages. We'll cover some of the pros and cons of the two-level inverter, multi-level inverter, describe some differences between a voltage and current source inverter, and then talk about modified versus pure sine wave inverters. We need to design the output stage for our power supply. In a previous video, we discussed how our filtered half-H bridge topology is very similar to the output stage for an inverter. I thought it would be a good idea to dive into some details about inverters and inverter topologies. Learning more about inverter output stages may lead us to learn more about possible architecture implementations that we didn't think about before. Now, let's talk about the elephant in the room. No, not that elephant. Voltage source inverters and current source inverters. Why are there two types of inverters? Well, this may not come as a surprise to you, but the difference between a voltage source inverter and a current source inverter is very similar to the difference between a simple voltage source and a simple current source. The switches look very similar between the two topologies in practice, with a high and low side switch on either side of the load to V plus and V minus, so that either side of the load can be connected to the high or low side of the supply. The difference here between the two topologies is that with a voltage source inverter, the switches connect one side of the load to one side of a voltage source, and the other side of the load is connected to the other side of that voltage source. With a current source inverter, the switches connect to either side of a current source. In practice, the current source can be implemented with a voltage source in series with a suitably large inductor, or another means. Since the torque output from an induction motor is almost directly proportional to current, a current source inverter could easily be used to drive an induction motor at constant torque. A couple other notable properties, since we're regulating to a current set point, short circuits on the output or shoot-through in the switching FETs has a limited effect on this circuit. If you don't know what shoot-through is, please look back to our previous video where we described shoot-through in detail. With that said, the current source inverter operating principle relies on a minimum load current and has a lower maximum output frequency than a voltage source inverter. Specifically, the light load, high frequency mode of operation is especially unstable. I mean, that it has some pros. The current source inverter has some pros, but I just don't think it's going to work for our topology. We need our power supply to operate under light load and have good transient voltage regulation performance, so the current source inverter is pretty much out. What about the voltage source inverters? Voltage source inverters use a fixed DC voltage and pulse width modulation to regulate the output voltage. They ultimately create the output voltage by setting the output as a function of the input voltage times the duty cycle at any moment in time. How the voltage regulation actually occurs is a task for the control algorithm and isn't really a concern for us right now when we talk about the power output stage. The stability of this topology is not dependent on the load, and really has less stability criterion than the current source inverter, just the typical gain and phase margin required for any control loop. These are typically what are used in voltage regulators, like an inverter output, since they regulate voltage. It seems obvious when I say it like that, but I'm just saying something obvious in hopes that it makes the point easier to remember. So voltage source inverters then. They just switch between VCC and ground to produce an output voltage? Well, they can. But if a person wanted to reduce switching losses, reduce electromagnetic emissions, or improve efficiency, multiple DC voltage levels can be used to reduce the switching losses and reduce the required change in voltage per second. The switching losses are reduced because when the switch first turns on and begins to conduct current, the voltage across it will be reduced, and so will the power dissipated in it. Since our PWM is extrapolating between smaller jumps rather than VCC and ground, the ripple on the output of a multi-level voltage source inverter can be significantly reduced as well when compared to its two-level voltage source inverter counterpart, since there's less noise in the signal before it actually gets to our power filter. Another benefit here, since we actuate our silicon switches in the same amount of time but have a smaller change in voltage, fair warning, the following sentence will contain words only familiar to persons tortured enough to experience differential calculus. The radiated emissions has the potential to be reduced since the dV/dt has decreased. For the layman, the radiated energy that could knock out your Wi-Fi, cell phone reception, and walkie-talkies may be decreased by switching less voltage on and off in the inverter output stage. May be decreased is a careful choice of words, since not all high-frequency noise on a board can find a coupling mode to escape the board, and it's very easy to create accidental antennas on a PCB just perfect for radiating this energy. Generally better to design in provisions to reduce electromagnetic interference or the radiated energy coming off of a board, even if you don't expect them to be necessary for a particular signal, just in case. When multi-level inverters provide efficiency gains and better electromagnetic performance, they come with some big drawbacks, some of which we'll talk through now. First, a more complex control scheme, since you'll need at least one switch for each of those additional voltage levels used in your system. More switching elements capable of handling the currents at play, which increases the cost of your design. A need for more high current routing on the PCB is also introduced, and that'll directly increase the physical size of your board. Last but not least, you need to add a cell balancing circuit to maintain the voltage levels required for each inverter level across each leg of your capacitor bank, besides the added cost of the extra capacitors. Since some of the largest benefits of the multi-level inverter topology over the two-level are improved efficiency and lower output ripple, let's move forward with the two-level filtered H-bridge topology for our proof of concept platform. This will give us a chance to evaluate the ripple and efficiency of the topology. Then we can decide whether the complexity of the multi-level topology is warranted given our ripple and efficiency requirements in the future. Given that our efficiency requirement is efficient enough to not overheat under full load or explode, I expect a good thermal design may be able to circumvent the need for a multi-level output stage topology, just so long as we don't encroach on our runtime with our power supply in the final implementation. Okay, one more thing to discuss. Pure sine wave versus modified sine wave uninterruptible power supplies. These supplies implement an inverter stage, but they use a very different operating principle. In a power plant somewhere near you, it is very likely that your power is generated using a spinning motor that takes in mechanical energy to create electrical energy. This motor is spun at exactly 50 or 60 hertz depending on where you live, and this voltage is regulated to, well, depends on where you live. This gets distributed all throughout the world through high voltage wires and then is stepped down near each load, read home or business, and the way that this motor is constructed provides smooth sine waves at the desired frequency and voltage at the output, due to the way that the magnets come in and out of alignment with the motor windings as it physically rotates. I'm calling this a motor, but due to the application, generator is technically more applicable. Motor is just easier to conceptualize, and there's very little difference between the two in theory. In practice, there's some differences. At its core, a motor or generator uses a voltage to create what is effectively a static magnetic field, interacting with what is effectively a rotating magnetic field, and this difference produces a physical mechanical rotation, or vice versa, turning a mechanical rotation into a voltage. There are many different ways to do this, some involving permanent magnets and stationary windings, sometimes rotating windings, sometimes there's no permanent magnets involved at all. Motors, drives, and generators probably deserve 300 hours of explanation. However, I'll spare you the details for now. Long sidebar avoided, the pure sine wave inverter uses very precise control of the output stage, at the cost of more switching losses and more complex control, to recreate that sine wave very accurately. The modified sine wave doesn't. Some modified sine waves even go so far to output a glorified square wave and call it a sine wave. So, if I want to plug some equipment into an inverter, does it even matter? Do I really need a sine wave? Or is a stepped square wave enough? Well, the answer isn't simple. The differences between a pure sine wave and modified sine wave input is ultimately that there's energy contained in the power fed to the load at frequencies that your equipment may or may not expect. And this energy needs to be somehow absorbed or diverted by the input power filter of whatever's being plugged into it. That extra energy being absorbed or diverted may cause the electronics to run hotter than normal and may even cause some electronics to fail. At worst, that extra energy may couple through power supplies and cause your electronics to malfunction. Maybe your device will fail a little earlier. Maybe it will fail in 3 seconds. It all depends on how the equipment was designed. In most cases, even a square wave is fine for short periods of time. Key phrase: short period of time. If you look into any double conversion or AC to DC to AC converters, that'll supply power to the load using the inverter 100% of the time, they're all pure sine wave inverters on their outputs, and this prevents damage to the connected equipment. The short runtime 10 to 20 minute inverters can use those modified sine wave outputs, since 10 to 20 minutes of extra stress on a component is probably fine 99% of the time. That said, moving forward, I don't want to need to worry about overstressing any connected equipment. Therefore, we're going to move forward by building a pure sine wave UPS, rather than a modified sine wave UPS. Great step forward. The cat is out of the bag, and the beans are spilled for Project Darwin. You know what we're building, an uninterruptible power supply, and we are ready to move forward. We're well on our way with the proof of concept phase, so subscribe to be notified of our future videos where we'll walk through some great points like developing with the STM32 ecosystem, where to buy electronics components, and discuss stability criterion for control loops. If you're excited to build this UPS with us, let me know by hitting the like button on this video or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thanks for staying till the end. Bye!